Hi and welcome to this fifth video in the series on NMR spectroscopy. In the previous video, we came across a very important concept in NMR called as spin-spin coupling. And in this video, we are going to extend that a little to talk about coupling constants and how it helps us in interpreting NMR spectra. And towards the end of this video, we'll also be targeting to solve two spectral problems by elucidating the structure from the spectra. Okay, so just to give you a brief overview of what we've done in the lecture number 4, we discussed that spin-spin coupling is possible for magnetically non-equivalent nuclei, and secondly, they should be under the influence of each other. That means they have to be in a close vicinity such that their magnetic moments can interact with one another. And whenever these two criteria are met, the nuclei are said to couple with one another so as to bring about characteristic splitting patterns. And we discussed that the splitting in the signal would be to the tune of 2ni plus 1. That's the formula that is going to be followed, where n is the number of neighbors, I is the quantum number, the spin quantum number for the nuclei, which is coupling with the nuclei under consideration. And this formula just gets reduced to 2 multiplied by n multiplied by half plus 1 when you're discussing H1 nucleus or any other nuclei wherein the I value is exactly 1 by 2. And this just gives us a simple empirical formula of n plus 1 to determine how many peaklets will result when a certain nuclei couples with its nearest neighbors. What we also came across in the previous video is the ratio of intensities of the split signal. That is, that if at all you get the signal being split into two, then it would do so in the ratio of 1:1 with respect to their relative intensities. If at all it is being split into a triplet, then it would be 1:2:1, and so on and so forth. And we said that this is based on, typically for H1 NMR spectrum, this is based on the expansion of binomial 1 plus x raised to n. And if at all the coefficients of each and every term is considered in this expansion, the ratio of those coefficients is the ratio of relative abundance of individual peaklets that arise in the split pattern of the NMR signal. A simpler way to gauge this would be the Pascal's triangle, which we came across. And in Pascal's triangle, it's easier to identify what should be the relative intensities of these peaklets just based on addition of the two terms which appear in the preceding line. And that's how we said that you could get relative intensities of these peaklets possible as and when you have coupling with one nuclei which is a neighbor, two nuclei which are nearest neighbors, three nuclei which are nearest neighbors, and so on and so forth. Okay, so having discussed splitting patterns and the relative intensities of each peaklets, come to another very important concept in NMR called as the coupling constant, or the J value. Now, as you see in both these split patterns of the triplet as well as the quartet, as was observed in the typical NMR spectrum of the ethyl group connected to something, say for example, then you would get splitting patterns which have a quartet of a signal and a triplet of a signal. Now, the difference between the frequencies of individual peaklets also gives us some useful information about the protons which are undergoing coupling, and at the same time it can even help us in doing structure elucidation. Like, say for example, if we talk about cis coupling versus trans coupling, based on the extent to which the peaklets are differentiated from one another, you could be able to predict whether the olefin is cis substituted or whether it's trans substituted, and so on. So that's why this concept of coupling constant is very important, because it helps in structure elucidation. It gives us one additional information about the molecule, and hence it facilitates us to find out what is the resultant structure of the molecule whose spectra is being probed. Alright, so the next question we are asking is, why is it called a constant? And as the name suggests, if it is being called a constant, that means that it mustn't be changing with respect to certain experimental factors. Let's compare the same thing with shift values from TMS. And we've discussed this a few lectures earlier, that the shift from TMS is highly dependent on the operational frequency of the NMR. And that is the reason we require to define something called as a chemical shift delta, wherein we define this chemical shift value as the shift in hertz divided by the operational frequency of the NMR in megahertz, and we represent this in units called as parts per million or ppm. And this value of chemical shift is independent of the operational frequency, so irrespective of whether the NMR is recorded on a 60 megahertz instrument or a 100 megahertz instrument, you would get the exact same value of chemical shift. However, as you change the operational frequency of the NMR instrument, the shift in hertz is going to differ for each and every scan that is recorded in a different operational frequency of the NMR. So it's very, very clear that if at all we do not consider the chemical shift values and we just plot a graph which has a shift in hertz being represented, and if at all I run one NMR at 60 megahertz operational frequency and I run the second one at 100 megahertz operational frequency, then I'm going to see a difference between the shift values for the same nuclei when I record it at 100 megahertz operational frequency as against when I record it at 60 megahertz. So what I'm trying to establish here is that shift from a certain reference like TMS is dependent on operational frequency. That being established, let's look at what happens when to these split signals. So irrespective of whether the operational frequency is 60 megahertz or if the operational frequency is 100 megahertz, the spacing or the difference between the frequencies of these peaklets that originate due to coupling of protons remains essentially the same. Okay, and let's take a moment to sink that in. What I'm trying to say here is, irrespective of whether we are operating at a frequency of 60 megahertz or whether we are using a 100 megahertz instrument, the coupling constant J or the difference between the frequencies of individual peaklets for the peaks that are coupling with one another in a magnetically non-equivalent environment remains essentially a constant. So if you see the difference between spacings of these two to be about 7 hertz, or sometimes also given as CPS or cycles per second, you would see the exact same value for the difference between peaklets when you are operating at a higher field frequency of about 100 megahertz. Alright, let's take an example of some spectra that have been recorded. Now here you've been given two spectrums A and B of the same molecule that's recorded at two different operational frequencies. The first one is recorded at 60 megahertz and the second one is recorded at 300 megahertz. Now what you see is that if at all you compare the distance between the individual peaklets originating here at the 60 megahertz operational frequency, or if you do the same thing in an expanded version of the 300 megahertz, you would see that the values of this difference happens to be exactly the same. So irrespective of whether you are operating at 60 megahertz or 300 megahertz, the J values happen to be the same in each of these cases. And that's something which is very significant, because this value being held a constant can help us in doing some structure elucidations. What we've mentioned earlier is also the reason why whenever you're operating at higher field strength so that you can get good resolutions, usually to observe the splitting pattern you need an expanded version near that particular frequency where you want to observe the splitting patterns. And therefore in any normal NMR spectrum that is recorded at quite a higher field strength, you would see that all these coupling patterns are given only as an expanded form because the spectra itself is well resolved due to it being operated at higher field strengths. Alright, let's come back to our example of an ethyl substituted compound and look at the J values a little more closely in this particular example. Now what we observe is that the J value in this case for a proton designated as A and B, which are magnetically non-equivalent, is also given as a J3 coupling. And this is the notation used because the coupling happens across 3 bonds and therefore it's also called as 3-bond coupling. Also sometimes defined as vicinal coupling. So that itself prompts you to think that if at all there is a vicinal coupling, there will be geminal coupling and there will be coupling of long range called as long range couplings. Naturally, the geminal coupling is going to be of higher with higher coupling constants as compared to vicinal coupling. And as the distance goes on increasing between the nucleus that is being probed and the nucleus that can influence the nuclei that is being probed to split it, you would see that the values of coupling constant goes on decreasing. So highest would be the geminal coupling, also called as K2. You also have long range coupling that is possible. Okay, coming to what are the typical values of J observed in an H1 NMR. For H1 NMR, the J values range anywhere between 2 to about 20 Hertz. So you don't see a large difference between the peaklets when it comes to protons coupling with one another. Typically when the coupling is vicinal, you see a value of about 6 to 7 Hertz that is observed for coupling. Now, what are the factors that affect this value of J? The first factor which affects the value of J is the proximity of the nuclei that is undergoing coupling. So closer the two nucleus that is undergoing coupling, more is its effect going to be on the coupling constant value J. And it's sometimes not that simple either, because there is one more factor that affects the values of coupling constant. In the second one is the angle, also called as the torsion angle between the groups, becomes particularly important when you're talking about vicinal couplings between groups. So if at all we look at the couplings between A and B, where A and B are two different types of nuclei which are in magnetically non-equivalent environments, and the splitting of A with respect to B and B with respect to A would depend on the torsion angles made by these two nuclei. So in some cases where there is free rotation possible, you don't see the effect of torsion angles, but in some cases where then you would see some typical effect of the angles. Okay, so based on all the information that we've collected so far, let's see if we are able to assign structures to these two different esters. So what is given to us is that they are acetate esters. Both of them have molecular formula C5H10O2. They are isomeric, and we need to find out what is the exact structure that gives us the first type of spectrum, let's label that as A, and the structure that gives the second type of spectrum, B. Okay, to be able to do that, we are going to be using not only the chemical shift values, we are going to be using the couplings involved so as to determine the nearest neighbors, and then eventually we'll also be using peak integration. And in this particular spectrum, the J values haven't been given, but for more complicated structures whereby it is more difficult to predict which protons are the nearest neighbors, etc., then the coupling constant values can also help, because the coupling constant values are the same for two nuclei that couple one another. So that becomes a useful tool to decipher which are the two nuclei which are undergoing coupling. Okay, let's start by doing the simple peak integration so that we are able to identify how many protons result in individual peaks in that particular spectrum. So if, say for example, we are looking at spectrum A, and after peak integration you see these values written right below the peak. Okay, so you have 1.76, 2.64, 1.78, 2.59. When you total all of that, you get a value of 8.77, right? So this is the total weight of all the peaks that have appeared due to protons, and we've already been given in the structure that there are 10 protons. So if 8.77 corresponds to 10 protons, for one proton it should correspond to 0.87 approximately, right? So when you compare, 0.87 represents one proton, so 1.76 should represent how many, 2.64 should represent how many, 1.78 should represent how many. You get roughly 2H here, 3H here, 2H here, and 3H here. So that accounts for 336 plus 4, 10 protons overall in the molecule. So that helps us in predicting now that at about 0.9 ppm, let's take this as the delta value. You have the multiplicity and the number of protons, and what is our inference from that. So there is a peak appearing at about 0.9 ppm, and that peak is the one that has 2.59 as the peak integration, therefore it is a 3H and the multiplicity looks like a triplet. Likewise, at about 1.8 delta ppm, you have a 2H multiplet, and because it's a high resolution NMR, it's quite clear that the multiplet is a sextet. We'll remember that while we are inferring what should be its nearest neighbors. Then you have a peak at 2.2, which is a 3H singlet, and a peak at 4.1, which is a 2H triplet. So the inference that we can draw from this is that the 3 proton system should be next to a CH2. Only then this can appear as a triplet, right? Now the 2 hydrogen system, which is appearing at 1.8, should be next to a CH3 and a CH2, so that it can get a total number of proton count as 3 plus 2, 5. And if there are 5 neighbors, then this peak should get split into a sextet, as is clear from the NMR spectrum. Alright, a 3H singlet should be resulting from a methyl group that should be next to carbon atoms that don't have any hydrogen at all. And lastly, a 2H triplet should result from a CH2 group that's next to a CH3. Alright, on careful examination of all the delta values as well as the multiplicity of individual peaks, it looks like the most probable structure that could give an NMR spectrum of this type should be this acetate ester. And this acetate ester has distinct type of protons, and let's start labeling them from in this particular order: A, B, C and D, from the most upfield to the most downfield. Okay, so the hydrogens as a part of the methyl group should be the one that is most upfield, because it doesn't have any electronegative groups around it so as to push it downfield. And this should appear as a 3-edge triplet, and that's consistent with A here. Okay, so the next one is a 2-edge sextet, should result from this CH2 group that is flanked by a methyl group on the left and a methylene group on the right. Total number of neighbors are 5, and hence the peak should be split into a sextet, as it is evident from the NMR spectrum. The third one is resulting from a methyl group that is present next to an electronegative group, and that's the reason it's shifted slightly downfield to about 2.2. So this methyl group, which is at the termini of the acetate group, could be the one that could result in a peak at 2.2, which is not split because there is no neighboring proton for this methyl group. And the last one, which is pushed the most downfield, should be the one that is next to a heteroatom, and thereby its electron density is reduced considerably, thereby pushing it downfield. Not only that, it is next to a carbon atom containing 2 protons, and therefore the peak itself should be split into a triplet. So that's how we could do structure elucidation from the NMR spectrum. And I'll leave you to decipher the structure of the molecule that results in spectra B for yourself. The steps are simple. Peak integration first. After identifying the number of protons that result in the 3 peaks that are seen in the spectra from B molecule, you can then infer the nearest neighbors from the coupling patterns, and based on the nearest neighbors and the delta values, you can predict the structure of the molecule. The structure of the molecule finally comes to this. And you see that the molecular formula in each of these cases is exactly the same, but their NMR spectra are considerably different from one another, and these NMR spectrums will then help us in elucidating which of the 2 structures is correct for the ester that is taken at hand. Alright, so that's what we had as a scope for this particular video. I'll encourage you to go ahead and take up more examples of spectra and try to solve them based on the existing information. What we'll follow this up with will be principles of C13 NMR, and once we've discussed that, we'll go to higher order NMR techniques.